This is the first video in a new series called Math Competition Gems. In each one of these vids, I'm going to do one or two short competition problems. They're going to be interesting, of course. They will illustrate classic problem-solving ideas. And most of all, they won't be too difficult. They won't be mind-crushing. I'll leave the mind-crushing, super difficult problems for another series I'm working on, which is going to be called Mind-Crushing Competition Problems. Okay, so this is volume 1, and I'm going to look at one problem in this video today. So here's today's problem. We are given a quadratic integer 2 plus root 3, and the powers of this generate two sequences in the following way. Like this, 2 plus root 3 power n, this will be some rational part plus an irrational part like this. So a quadratic integer has a rational part and also an irrational part. And when you raise a quadratic integer to some power, you get another quadratic integer. So a1, a2, a3, this will be a sequence of all the rational parts. And then b1, b2, b3, that's the coefficient of this irrational number, bn root 3. And the problem is like this. We want to find the limit of the ratio of an over bn as n goes to infinity. To get some insight into the problem, it really helps to do a few numerical examples. So when n is 1, I raise it to the power 1. That's easy. I get 2 plus 1 times root 3. So a1 is 2 and b1 is 1. When n is 2, I square this. I work out the arithmetic. I get 7 plus 4 root 3. So a2 is 7 and b2 is 4. Let's do one more. N is 3. I get 26 plus 15 root 3. So a3 is 26. b3 is 15. Okay, you see what's going on here. I'm generating my sequence of a's here. And also at the same time, I'm generating a sequence of b's here. And let's do more numerical experiments. And this time I'll go farther using some computer programming and just show you how the numbers work out. Here's the output of a bunch of computations I did in Maxima. So here is my an, this is my bn, and here's my ratio an over bn. So it does seem to converge to 1.7 something. It doesn't go off to infinity. And my question to you is here, what do you think it converges to? Maybe you can take a guess. Take a guess, and shortly we will prove what this limit is, and then we will see how good your guess was. Since we have this 2 plus root 3 power n, it makes us think that perhaps we should use the binomial theorem. And the binomial theorem looks like this. We take x plus y and expand everything using the binomial coefficients. I can start off like this, n0, x, n, y0 plus n1, x, n minus 1, y1. And so on all the way up to n choose n, x power 0, y, n. And now I just substitute 2 and 3 for x and y. And I get this expansion. Okay, just a straightforward substitution. All right, let's look at this more carefully. If I take this term, you see the root 3 is gone because it's power 0. So this is actually rational. And likewise, this term is rational because it's root 3 squared, so no more root 3. So all the even powers of root 3, this leads to rational terms. Whereas all the odd ones, well, this is going to be irrational here, irrational. and this is irrational, and so on. So what I can do is collect my rational terms to the left and my irrational terms to the right. Like so. All right, so this whole thing here, this is all rational, whereas this whole part here, this is irrational. And I can factor out the 1 over root 3. I factor out the root 3, and I end up with bn times root 3. So I factor it out, and whatever's left, I call that bn. And here, all my rational stuff, that's an. That's very interesting, because I can now do an amazing trick. Now it's super easy for me to get it an expression for 2 minus root 3. All I have to do is take this and substitute minus root 3 for this, and it's right there. So I get this for free, an minus bn root 3, like so. Very nice. And furthermore, I have a formula for an now. An is 2 minus root 3 power n plus bn root 3, like so. So I know an now. Why is this good? Well, first of all, let's examine these things. Bn is always going to be greater than or equal to 1, because this is greater than or equal to 1. And all I'm doing here is adding more positive terms, so the result for bn has to be greater than or equal to 1. Bn is greater than or equal to 1. Now 2 minus root 3, that's greater than 0, but it's less than 1. So as n goes to infinity, 2 minus root 3 power n goes to 0. Okay, so this might really help me to simplify things, and indeed it really does. Okay, watch this. Let's get some more room like this. So an over bn, this is now like so, and okay, bn is greater than or equal to 1, so this denominator is fine. And now I can take the limit, but we saw a moment ago that this goes to 0, so this thing is going to go away. Bn root 3 over bn, and now I can cancel them. There's no problem because I proved this. Right, and so this limit is, let's get black back. This limit is root 3. And if we go back, we see 1.7 something. That was indeed root 3. 1.73205 something or other. That was the number we got earlier in that table that I computed with Maxima. And we are done. So if you like this, click like, comment, and subscribe. More of these competition gems are coming in the future, as well as my other series I'm working on, the mind-crushing problems. Okay, so I hope you like this, and I'll see you again next time.